All right. Good evening. Thanks for everyone staying for so long. This is the last and third lightning talk session. And we are going to start with Saronath Halder from the University of Warsaw with the talk Unextendable Product Basis and Multicopy Locally Indistinguishable Sets.
Yeah, thank you very much. Is it possible to see my slides?
Yes, it works. You could try to hide this label in the bottom.
Yes, okay.
And then let me, just before you start, sorry, Saronath, let me ask all other fellow speakers to mute themselves and also close the webcam while Saronath is speaking. I will do the same. Yeah, so Saronath, you have 4 minutes, please, go ahead.
Thank you. So I'm going to talk about this unextendable product basis, and basically I'm going to talk about the role of this type of basis to construct multi-copy locally indistinguishable sets. In this particular work, we can start with basically non-orthogonal unextendable product basis, but before non-orthogonal product basis, the orthogonal product basis was introduced in 1999 PRL paper, as I have shown here. Now, given a set of product states, not necessarily orthogonal, if they span a proper subspace of a Hilbert space, while the orthogonal complement doesn't contain any product state, then the considered product states are basically unextendable product bases. So the main theorem that we have proved in this work is basically this: if we consider any bipartite pure entangled state, then the orthogonal complement of that particular entangled state is spanned by a set of linearly independent product states. So this linearly independent product state, they span a proper subspace of the bipartite Hilbert space, while the complementary subspace is basically one-dimensional entangled subspace. So basically, they are forming non-orthogonal unextendable product basis of maximal cardinality. So basically, the proof procedure follows from a simple fact that in the bipartite case, if you consider this 0, 0, minus 1, 1, this is an example actually, then the orthogonal complement is basically spanned by plus, plus, 0, 1, and 1, 0, these three product states. They are linearly independent and they form a UPB of maximal cardinality in 2 cross 2. Following this particular thing, we can actually construct in D1 tensor D2 bipartite Hilbert space. Now we consider local state discrimination problem. In this problem, a quantum system is prepared in a particular state taken from a known set. Then the subsystems are basically sent to spatially separated parties. Their job is basically to identify the state of the system by doing LOCC, that is local operations and classical communication. Now, because of our theorem, we can actually construct a local state discrimination problem. That is, you can consider the UPB space and a projector, maybe a density matrix supported on the UPB space, and then you have to choose another state from the complementary subspace. So basically, you are considering a bipartite ensemble which is consisting of two orthogonal states but mixed states. So they cannot be perfectly distinguished by LOCC even if multiple identical copies are supplied. This is basically based on previously the proof process is basically based on this 2011 PRL paper that I have referred here. Now, because of our theorem, we can actually construct multicopy locally indistinguishable ensembles. These ensembles can have interesting applications in case of data hiding. Now, it was not known before that this type of ensembles can be constructed using non-orthogonal UPB. So the UPB connection that we have established here is new. Previously, because of orthogonal UPB, such constructions were there, but because of our theorem that we have constructed here, apparently different, there are several multipartite multicopy locally indistinguishable sets which are apparently different, but they are actually connected through the notions of UPB. This is what we have tried to establish in our work. So this is it. This is the main result of our work. The collaborator is Dr. Alexander Streltsov from Center of New Technologies, University of Warsaw. Thank you.
Thank you very much for the talk and also for keeping the time. I don't see any questions in the chat or the Q&A. My question is very naive. So is there any motivation behind this work, or is there any connection to applications like quantum communication?
Yes, this is what I was trying to do, is that, for example, locally indistinguishable sets are basically applicable in case of data hiding, right? Basically, this type of ensembles, they are multi-copy locally indistinguishable. So this type of ensembles, if you use, then dishonest parties, they cannot be able to extract the information encoded against these states, even if there are identical copies of the quantum system. So you can say that these exploring this type of ensembles are really very important from practical purposes.
Great. Thank you very much. Thanks for the nice talk and for this informative answer.
Thank you.
Yes, we have to move on to second talk. Is going to be given by Carlos Efrain Quintero Narvaez. Carlos,
yes.
Could you please share your slide?
Yeah, let me do it.
Carlos is from Universidad Nacional Autónoma de Mexico. And the talk is entitled Qudits and Non-Commutative Tori. Would you like to switch on your microphone? So your webcam, or it's better?
Sorry, I don't have my webcam isn't working exactly. Sorry.
Okay.
Yeah. Okay. So let us consider a qubit, and we know it. Is the quantum analog of a classical bit. While a classical bit can have one of two values, 0 and 1, a qubit can be in a superposition of two quantum states, ket 0 and ket 1, which is of the form this linear superposition, with alpha and beta such that their magnitude sum to 1. In exchange, a qubit is the quantum analog of a classical digit in base d. That means d as a natural number. And while a classical digit in base d can have one of the values in 0, 1, and so on until d minus 1, a qubit can be in a superposition of the quantum states ket 0, ket 1 until ket d minus 1. A superposition of the form like this, with a linear combination of these states. And this linear combination is such that, the magnitude of the coefficients sum up to 1. So we have a generalized qubit, right? By having a qubit. So let us consider the state space of the qubits. This is usually a two-dimensional Hilbert space, which is morphed to the complex numbers c squared. So when we consider a system containing n qubits, it is described as the tensor product of n copies of this Hilbert space. So this in turn is a 2 to the n dimensional Hilbert space. So the space of all possible qubit states is a d-dimensional Hilbert space. And thus we can consider a system containing n qubits and which is described by the tensor product of n copies of the d-dimensional Hilbert space. This is as shown here. So in turn, this is a d to the n dimensional Hilbert space. The set of transformations that can be done to a qubit are the symmetries of the two-dimensional Hilbert space. So these transformations form a two-dimensional unitary group U2. Each of the elements of U2 is represented by a 2x2 unitary matrix with complex entries. So we refer to this transformation as quantum gates. Now for qubits, the set of transformations that can be done to a qubit are the symmetries of the d-dimensional Hilbert space. So these transformations from the d-dimensional unitary group, UD, and each of the elements of UD is represented by a d by d unitary matrix with complex entries. We refer to these transformations as qubit quantum gates. Now let's see some qubit and Qudit gates. Consider the X Pauli matrix as a qubit quantum gate, this 2x2 matrix. So see that this gate has the property of exchanging 0 and 1. Give it 0 and give it out 1. We give it 1 and we get it out 0. So this we can also see as if it adds 1 to the basis states using, like shown here, using the addition mode 2. And also note that x squared is equal to the identity. So now we generalize this X gate to work with qubits. So we have an X sub D gate that adds 1 to the values of the basis states, which is shown here, and it is done using the addition mod D. Thus, the matrix form of XD is this one shown here with like the first column moved into the last column of the entity matrix. So this is the XD matrix. Also note that in this case, XD to the power of D multiplied D times is the identity. Thus, now consider C Pauli gate. This is the gate shown here. This gate flips the face of 1 and leaves 0 untouched. Also note that C squared is the identity. Thus, we can generalize the qubit seed gate to qubits by finding the gate CD that changes the phases of the basis states conveniently. For this, consider CD acting on a basis state, and it adds this base depending on this phase depending on which state it acted upon. So the matrix form CD is this one shown here, and CD to the power of D is the identity. Now consider the Hadamard.
Sorry, Carlos, you are at 5 minutes. Please wrap up in 1 minute.
Yeah. So we shown here this that the Hadamard gate can be used to generalize with the quantum Fourier transform, and we get this basis of superposition states. And at the end, we showed that all this business with the matrices can be simplified using space-time algebras. We use this relationship here with the Pauli matrices, and we put them into an algebra that only uses the relationships. And finally, this can also be done with the qubits using this structure called the noncommutative Tori, where we use CD and XD as the generator elements, and thus that is done. This does the same thing as the space-space algebra, but with qubits, and simplifies all of the matrix operations we do. That's it.
Thank you very much, Carlos. In the interest of time, we have to move on to the next talk. Thank you. The next talk is from Eduard Zubov from Kyiv Academic University, Ukraine. And Eduard will talk about the quantum origin of exchange bias in compensated rare earth ferrimagnets. Eduard, could you please share your
Uh,
slides?
can I put my presentation?
Please do.
It is seen?
We don't see it. Could you please share your screen?
No.
Mm-hmm. Yes,
okay.
It works perfectly, yes. So please, go ahead.
Full screen. Can I make a full screen?
Well, for us it is. So it looks like full screen for us.
It looks like that? Okay. Thank you very much. The topic of this presentation is quantum origin of exchange bias in compensated rare earth ferrimagnets. This work is the result of a long-term collaboration with colleagues from the Institute of Physics of Polish Academy of Science. You can see, next slide. Okay.
Yes.
Arteferrite erbium or iron oxygen 3 has attracted renewed attention in recent years due to the discovery of its remarkable properties. This compound demonstrates interesting phenomena of negative magnetization and associated fast switching between two coexisting states with negative and positive magnetization. In Fig 1, the hysteresis loops of erbium, erbium iron oxygen 3 in magnetic field up to 10 kHz is shown. One can see the asymmetrical shift of hysteresis loop for different cooling protocols. This phenomenon is named as exchange bias. Next slide. The origin of this phenomenon is mysterious, and discussion on this question are continuing so far. It is important to note that in this case we have unidirectional anisotropy. Earlier we proposed the model with quantum magnetic Hamiltonian depicted in this slide. In mean field approximation, it is easy to find to make the Hamilton diagonalization, and with a general quantum axis tilde z. In this Hamiltonian contains isotropic symmetrical exchange interaction, also anisotropic term, and asymmetrical anisotropic exchange Doloshensky-Moore interactions and rare S and iron exchange interactions. We surprisingly, the presence of anisotropy exchange interaction between rare transition metal ions and iron causes the deviation of quantum axis from normal to FM axis L. This one can see in the next Fig 3. Next. In Fig 4, one can see deviation of quantum axis from normal, from this normal, and this quantum effect, it is observed for this system. For Hamilton, okay. For Hamiltonian parameters to be determined from experimental data, it was built the angular dependencies of free energy for different magnetic fields near the compensation temperature. See Fig 5. One can see that there is always potential barrier between two equilibrium states. It is supposed that the system is divided in magnetic clusters, superparamagnetic particles, in which the rotation of AFM axis is realized because the potential barrier height is considerably smaller the temperature T of order compensation temperature. In suggesting that we have positive magnetic field, the dominant relaxation time determines the sign of other parameters of order as total, to be connected with relaxation magnetization from iron and erbium subsystem. The instant magnetic field action determines the deformation of iron magnetic umbrella. Comparing the stable state in Fig 6a and 6b, we can see the appearance of unidirectional anisotropy. In Fig 6a, the positive energy of iron umbrella deformation is added to Zeeman energy squeezed umbrella. In Fig 6b, this energy is subtracted from this Zeeman energy stretched umbrella.
Sorry, Eduard, we are at 6 minutes. Could you please wrap up in 1 minute?
Okay.
Thank you. Thank you.
Thank you very much.
Okay, thank you very much. In the interest of time, we have to move on. Thank you for being here and for the nice talk. The next speaker is Andras Nemeth from Utrecht University. Andras.
Oh, hello.
Can you please,
can I share my screen, please?
Yes, if Eduard unshares, I think.
Okay.
Eduard, could you please unshare your screen?
I think Eduard is not here.
Then maybe our host, Ludovic or Maninder. Can Andras share his screen? Andras, please try and we'll see.
I'm trying to click on this button here, but it doesn't work.
Okay, so I think we need some help from our hosts.
Okay. Okay, now I can click share screen. Okay.
So Andras, we talk about borders between quantum and classical systems, the Gothendieck-constant.
Can you see my screen?
Yes, it works.
Okay, thank you. So let's talk about the borders between the quantum and classical physical systems. It's an important question. How far can we push our system of interest to keep its quantumish property? Of course, it's a very important question because we want to use quantum entanglement. It's a more complicated question than we can just discuss here, but we have some theoretical numbers which we can impress this feature. Measuring quantum entanglement is possible through Bell measurement. So here is the original Bell inequality, which we can generalize to a more mathematical formula. And if we are looking closer to this theorem, we can see that physical system can be classical and quantum mechanical as well. But we have more than these two types. We can separate the quantum state, or we can describe with a local hidden variable model. Of course, we want to use such a state which is entangled, and there is no any kind of local hidden variable model. That's the full quantumish state we want to use in any kind of quantum computing process. So the generalized Bell inequality, as you can see here, it's up to an n measurement setups where we measure in a bipartite system, and we can get alpha and beta as the results. This, as the Bell theorem says, there is a local upper bound to this state, which we can describe local and deterministic model. If we use this A and B's are plus and or minus 1 with the same matrix. So yes, if we put a mixed state which contains the fully entangled Bell state as or this well-known state, and it messed up with some free density matrix with some factors. Of course, it's normalized with this method, and if we just put inside the generalized Bell inequality, we get this nice inequality, which is not new, but not in this side from quantum theory, but the Banach space theory from the late 50s. It was a great mathematician called Gothendieck, and he said there is an upper bound for this matrix with some constant, this magical constant, and it turns out for the Werner state, the critical visibility is this Gothendieck-constant with the dimension 3. Yes, so it's a magical constant, and we can say if this, so our visibility is lower than this value, we have a quantum state which can be described by a local hidden variable model. So we want to avoid that state, of course. Okay, so calculation of this magic constant is my main task.
We are at 5 minutes 30 seconds, so please wrap up in a minute.
Okay. So how can we calculate this? So no analytical or quantum algorithm exists yet, so we have to brute force calculate this. We can use on the left side some nice solution, select some nice matrix, and the hard part is calculating the right side. So as you can see, there is a calculation binary tree where we just go through all the possible values and select the maximal value, and it's an exponential hard task. That's my main task. Currently, the most precise value is this value you can see here. For the Gothendieck-constant and inequality, there is a Wikipedia site where you can check this value for some interesting thing. This 92 size of the matrix is calculated in 3 months. So if we want to calculate one more bigger size, it takes 6 months and so on. So it's very hard task. Currently my other laptop calculating this also.
We are at 8 minutes, so let me stop using my version.
Okay.
I apologize. And of course, we can ask any questions. Let's move on. We still have 4 talks to go, and we are already past 9 o'clock in the evening. Marcin Jastrzębski is the next speaker from the University of Warsaw. Near-infrared femtosecond impulses, ultra-resolution spectrometers, and their applications. Marcin, are you?
Yeah, I'm here. Can you hear me?
Yes, we hear you. Share your screen.
Okay, so let me just share my screen. Okay, can you see my screen?
Yes.
And can you see the presentation?
Yes.
Okay, so thank you very much. Today I will briefly talk about what we are doing in our lab. So my name is Marcin Jastrzębski. I'm a bachelor student in physics from Poland, and we've been working on an experiment with my colleagues in the Center for Quantum Optical Technologies from Warsaw. So let's just jump right into it. We've been measuring femtosecond impulses, which are very short impulses of light from a laser. And to give you an idea what I'm talking about, we have a single copy of a very short impulse, and we split this copy into 2, and one of them is we split it on a beam splitter, and one of them is shifted in time and the other in frequency. As you can see, the bottom one is blue. It symbolizes that it is different frequency. And we measure the visibility of the interference in Hongu-Mandel interferometer. So let me just show you that when we have one copy of an impulse and the other shifted in time a little bit, the more we shift them, the less they overlap. And that's how we can measure the temporal width of the impulse. And also, if we do it in the frequency domain, we can shift in frequency and therefore measure the spectral width of the impulse. So quickly about the setup, on the picture on the left, you can see a collimator on a table, and there is a stepper motor. So we use it to create those time delays. And on the right, we have an electro-optical phase modulator, and we use it to create frequency shifts. and we can control them. We change them during our experiment. And as you see in this setup, we don't use any nonlinear effects, which are very inefficient energetically. And also we use a high-resolution spectrometer for the calibration, so that we know how to convert voltage in the circuit that we apply to frequency shifts, so we can calibrate our setup and then perform single photon measures without using a spectrometer. And as detectors, we use single photon detectors or photodiodes. And now quickly the results. Here we have a map. You can see probably here there is time shift in picoseconds, and then there is frequency shift. And we measure the visibility of two-photon interference, which is in this case just correlations. And we can see from this map, okay, how much we have to shift so that there is no more interference, and we can see if this impulse is chirped. In this case, it's not inclined or anything, and we can see the spectral and temporal width of the impulse, and here we fit a proper function to get those values exactly. So just to quickly summarize, it's a new method. No nonlinear effects are necessary. We can use single photon detectors or photodiodes, and we control everything electronically. Thank you very much for listening.
Thank you very much, Marcin, for the talk and keeping the time. Since it's very late, let us give questions, and let's move on to the next talk. It's going to be given by Samuel Kern from Comenius University with the title "The Transition Regime Between Traveling Wave and Resonant Parametric Amplifier." Samuel, are you ready to share your screen?
Yeah, I'm ready.
Thank you.
It should be visible now.
It is going to be visible soon, I think. Yes, it works.
Okay, so good evening to everyone. Let me talk about experimental tool, which is a parametric amplifier. Parametric amplifiers are becoming nowadays very important part of demanding experiments like gravitational wave detection or qubit dispersive readout. The advantage of parametric amplifiers is great noise performance and possibility to produce squeeze state and to squeeze noise. Superconducting parametric amplifiers, which are important for quantum experiment, can be divided into two groups. One is resonant parametric amplifiers, and the other is traveling wave parametric amplifiers. The resonant parametric amplifiers uses nonlinear resonator for interaction of strong driving pump with amplified signal. To enhance this interaction, a high quality of the resonator is used, but this high quality also limits the bandwidth of such an amplifier, which is typically about 20 megahertz. On the other hand, in traveling wave parametric amplifier, the parametric interaction is enhanced by a long time which the wave spent traveling along the amplifier. This parametric process can be understood within a nonlinear optics and can be described by coupled mode theory. For traveling wave parametric amplifiers, this theory predicts a large bandwidth and also very important conditions, so-called phase matching condition, which if is fulfilled, a very high gain can be observed. Recently, in last years, people mastered achieving these phase matched systems, and indeed a high gain was observed, about 20 decibels. However, obviously a very rapid oscillation in transmission is observed, and it seems to be unavoidable. And also the bandwidth of these peaks is about megahertz or 10 of megahertz, and the bandwidth of these peaks also seems to scale with the length of the waveguide in the same manner as a Fabry-Perot resonator or step impedance resonator. So what we did, we looked for origin of these ripples, so-called gain ripples, by the modifying of coupled mode theory, now including the reflection. We obtain technically same result for gain and bandwidth as a standard coupled mode theory, but now it is corrected via reflection coefficient, which we also shown that it originates due to amplification itself, as the amplification changes the impedance of the waveguide, and so it is very hard to avoid such a reflections. Also, what we would like to suggest is somehow a change of paradigm for parametric amplifiers to make use of advantage of both resonant and traveling wave parametric amplifiers, as we shown that the reflection enters the gain in positive manner, that the reflection enhances the gain. Also, we made measurements on Josephson junction traveling wave parametric amplifiers and high kinetic inductor and superconductor parametric amplifiers, and we compared our theory with the result, and we obtained a nice agreement with measured data. And it is all I wanted to say.
Thank you very much for a nice talk, and also for keeping the time. Since we are running late, we will not take questions. Thank you very much. We can move on to the next talk, Jure Brence.
Yes, hello.
Jure, are you ready to share your screen?
Yes, I am.
So Jure is from the Josef Stefan Institute from Ljubljana, and he will talk about boosting the performance of quantum annealers using machine learning. Please, go ahead.
All right. Good evening to everyone, and thanks for having me. So, quantum annealing is a paradigm of quantum computing that already offers real-world applications on up to 5,000 qubits. However, it is limited to optimization tasks. Now, one of the limitations of quantum annealing, when it comes to the size of the problems that we can solve, comes from noise. The way we understand it is the Hamiltonian that the device actually works with is not exactly the same as the Hamiltonian we send to it, because a random noise gets added to it, and also a form of systematic noise is added to it. And this systematic noise comes from differences between the physical qubits that come from imperfections of the device when in manufacturing. So our idea is to try to calibrate the input to correct for this systematic noise. And the way we do this is we add a small calibration matrix to our input Hamiltonian. We measure the performance of quantum annealing with success rate, which you can interpret as the probability of finding the ground state in one run of quantum annealing. We developed two algorithms for what we call adaptive quantum annealing correction. We start by sampling many calibration matrices using Latin hypercube sampling, which is a form of random sampling for high-dimensional spaces. We then evaluate the performance of each of these calibration matrices by performing quantum annealing with it. Now, the argmax strategy is to simply take the best calibration matrix among the ones we evaluated. This is the matrix that gives us the highest success rate. The second strategy, the predictive one, is more involved. We take all this data and we train machine learning models to predict the annealing performance of a given calibration matrix. Once we have a model, we can use an optimization algorithm to find better candidate matrices, possibly beyond the set of the ones we evaluated. And finally, these new candidates also need to be evaluated on the quantum annealer, and we select the best one. We performed experiments on a physical problem of electron ordering in Wigner crystals, and this is represented as a fully connected graph, which is the most complex problem one can solve on a quantum annealer. And we worked with 3 system sizes, going up to 360 physical qubits. And for each of these systems, we sampled 10,000 calibration matrices. We tried a number of different machine learning methods, and it turned out that for us, simple linear regression worked the best. Now, the results are very encouraging. For the smallest system, we double the success rate using our methods. For the middle-sized system, we increase it by a factor of about 4. And for the largest system, we improve the success rate by about 3 orders of magnitude. So we believe that this method can be put to good use by practitioners who struggle with issues of noise in their quantum annealing applications. And that's it. Thank you.
Thank you very much for a nice talk and for keeping the time. We have to move on to the last talk of the session. Thank you, Jure. The last talk is going to be given by Alan Santos from Stockholm University. Title is Conditional Coherent Control with Superconducting Artificial Atoms.
Okay, can you see my screen? Right.
Yes, we can see it now.
Okay, thank you. I would like to... Okay, let me away. Okay, thank you so much for all organizers for giving me the chance to present this work today. And I will present this works. More details can be found in archive. But this work is a Brazil-China interaction. Okay, as an experiment and theoresis work. Okay, and this is the contents. But let me move on. Okay, the system is a superconducting chip. Okay, maybe I don't need to motivate why superconducting qubits for our audience, but this is the system. Okay, we have actually 2 qubits coupled each other throughout coupler. Okay, this coupler is a frequency-to-enable qubit. The qubit 1 is also a frequency-to-enable transmon qubit. Okay, and the system schematically is like that. Okay, and here's the Hamiltonian. Okay, here I'm presenting the full Hamiltonian. Okay, I'm not choosing the system for 2-level system, and I will explain why. Okay, so if we take one 2-level approach of the system, okay, this is the Hamiltonian. The Hamiltonian becomes like that, and we can control the interaction between qubit 1 and qubit 2 using a farther tuned coupler. Okay. The figure is a little bit wrong, but the coupler is farther tuned of the system, and effectively you have a Hamiltonian, a Hamiltonian like this equation, and you have a swap in term between the qubit 1 and qubit 2, and this effective coupling is controlled by the tuning of the coupler. Okay, and also for the coupler state. Okay, it's important to say that if the coupler is in the ground state, mostly of papers do that, you can simplify the analysis. But when the coupler is not in the ground state, he can be excited. There is a correction in the effective coupling. Okay, so what we do here is to characterize the system. So we use this approach to try to find the experimental value of the effective coupling. Okay, we do this map. This is experimental data, and when you use exactly the equation given by the 2-level system prediction, we have a difference between the theory and the experiment. When the coupler is in the excited state, in the ground state, everything works well. But in the excited state, we have a problem. So how to solve this problem? To solve this problem, we need to take one three-level approach of the system. So you need to go back to this Hamiltonian, consider all levels, and late you can truck the system to a two-level system. By doing that, you have this correct, effective coupling, and when run again the experiment, you can see exactly one perfect agreement between the theory and the experiment. So as an application, we use that for implementing a coherent conditional control of quantum information in the system. Using the same system, for example, when you have the coupler in the ground state, we adjust the frequency of the coupler, and in the ground state, no information can flow from Q1 to Q2. But if you excite the coupler, you can allow information exchange between the Q1 and Q2 in a coherent way. Okay. So in conclusion, we don't need to consider superconducting qubits as a genuine qubit. You need to consider it an atom, and late you can move on to qubit approach. Okay. And as application, we ask or we affirm if we have a quantum transition for transmon qubit processors. Thank you so much.
Thank you very much, Alan, for the nice talk and for keeping the time. And with that, it's time to conclude the session. Thank you very much for all the lightning talk speakers of these 3 lightning talk sessions. And also thanks a lot for all the invited speakers speaking earlier today. Also many thanks to the audience, especially those who made this heroic effort to stay until the end. It's great that we still have 25 people in the session. Even though it was a bit tiresome and also a bit late, but I'm very glad that we had this lightning talk session, because it was a great way to get a glimpse of what's going on in the Eastern European area in terms of quantum information on the theory side and the experimental side. So I really enjoyed this. This 4-minute format is a bit different from the standard conference presentations, but I think, it requires different skills from those. But I think it's a nice way to concisely present your results. And maybe as a last remark, I just want to highlight that tomorrow the event continues. So we will start at 9 o'clock in the morning, Central European time, with workshops, quantum programming workshops, and then we will have various industrial, technological, business, and societal aspects of quantum technology during the day, covered by invited talks as well as panel discussions. So that's all from my side. Zoltan, did you want to add something?
No, I completely agree with you that despite that it's so late, it was really good to see all these things. So
great.
Thanks a lot.
Good. Thanks, and hopefully see most of you tomorrow as well. Goodbye.